Greetings to the DENSI Selection Committee. My name is Michael Blair, and I teach English Language Learner Physics, Conceptual Physics, and Physics A at Herbert Hoover High School in Des Moines, Iowa. In the following video clips, you will see how I use Discovery Education to improve my 90 minutes of classroom instruction. Because this is physics, I feel that everything should be hands-on and it's primarily lab-based. We watch Focus in Physics, Simple Harmonic Motion, discuss what we see, then students go to lab, and at the end of the class period, I take about 10 minutes to summarize the concepts that they learned and how we use those concepts in society. And finally, I'd like to say thank you to the Discovery Education who puts on the DENSI workshops. They're incredible. I have never been to such intense workshops in my life and learned so much from so many great people. It's 24/7 learning. Thank you again.
Is a type of periodic motion that occurs when a force on the object is proportional in strength but opposite in direction to the displacement of the object.
A restoring force is the force that brings a system back to equilibrium.
Imagine a pendulum. When the pendulum is shifted to the left or to the right, gravity acts as the restoring force, trying to pull the pendulum back to its central position. This force attempts to...
You did before.
You ready? Yeah. Okay, go ahead. 1, 2, 3, 4.
I feel like it's go farther here. Like this.
8, 9. Yeah, that's fine.
Still need to work on 19B. We'll have a little bit of time on Thursday to do that. Okay, I want to talk a little bit about what you guys found out in your lab. Did you notice a significant amount of difference in time when you let go of the pendulum here or whether it's up here? Did you notice a significant? Did you notice a huge amount of time when you had a lot more mass on this? Okay. Did you notice a lot more difference when it was shorter or longer? Which one had the greatest effect? Okay. I'm glad you said that because with your lab, no, that is perfectly correct. With your lab, they were trying to demonstrate to you that going at 10 degrees or 30 degrees made no difference. Okay? Having mass on here makes no difference. The only thing that makes a difference is how long the string is. That's what we were trying to get at. So if you go back and look at your data, you might find, yeah, there's a little bit of difference between here and here, but like you guys just said, this is really what makes the difference. And these properties became extremely useful about 400 or 500 years ago. The story goes that Galileo was sitting in a church on Sunday in Florence, and he noticed the chandeliers were swaying back and forth in the wind. And of course, being in church, it got to be really boring. I mean, it wasn't like an hour and a half church. These were like 3-4 hours long.
Wow.
Yeah. Okay.
Praise the Lord.
Okay. Praise the Lord. No, it wasn't even that kind of church because you sat there and you listened to people talk for hours and hours, and then you'd go eat, then you go eat, and then you'd come back and do the same thing. That's right. It's mass. Okay, it's church mass, not physics mass. Galileo noticed that heavy chandeliers, light chandeliers, if they were the same length, went back and forth at the same period of time. That If you had longer, shorter chandeliers, didn't matter what kind of mass they had, didn't matter if they swayed a little bit like this or swayed a lot like this in the wind, they had different periods of time. And he tested this with his own watch. Didn't have a little watches back in those days. He used the pulse of his body to figure this out. Okay? When church finally broke up, he could go home, he started to experiment with this, and he started to play around with these, with pendulums and things like that, and realized then, once again, like what we did for our lab, you can have a heavy mass, you can have a little mass, you can have it like this, have it like this, they're all going to go the same amount of time, same period. The only thing that makes a difference. Let's talk a little bit about why that is. If I let go here, compared to letting go here, which one travels the fastest? Which one has the highest velocity? The higher degree, right? Yeah. Okay? And so you would think, oh, well, okay, this guy's got to have a faster time. No. Because, exactly, he has much more distance to cover. Okay? And so he has to go faster. Same amount of time, larger distance, more velocity. Here, lesser amount, distance, don't need as much time, okay? Don't need as much velocity, same amount of time. Okay? Now, tell me, I have a big bowling ball and a little marble. We ignore air resistance. We go climb on top of a building. We let go. Who's going to hit the ground first? Both at the same time. Okay, is this pendulum falling?
Yeah.
The answer begins with the Y and ends with an S. Okay, it's falling to earth, right? But it can't go a nice straight down line, so it goes at an angle. But it's still falling to earth. Okay? Not at 9.8 because it's not straight down. It's at an angle. It's less than that. Those of you folks that take the Physics A class in 2 years, we'll play around with this. You'll see it's a trig function kind of thing. But we can calculate exactly how fast it falls. By that time, you guys will think trig's not that hard. All right. So this guy's falling, just like the marble and bowling ball. You can have massive weights on here. You can have hardly any weights on here, and it will still go at the same rate. Okay. So the only thing left is this, and this, you guys have figured out, significantly changes the period of time. Now, Galileo wrote this up and didn't do a whole lot with it. But word got out, you know, back in those days they write scientific papers and only a few people would actually get to see them. But they spread throughout Europe, and the Dutch realized, wow, this is just what we're looking for. This is a huge navigational cable.
Now we're going to do a compression wave. Now we're going to do a transverse wave.
I don't feel safe being videotaped.